All right, let's look at what happens when we do electrophilic aromatic substitution on an aromatic molecule that's got one substituent. All right, so it's a monosubstituted aromatic. And the example I'm going to show is nitration of toluene. So here we got toluene, we have nitration conditions. Remember, HNO3 and sulfuric acid are going to generate NO2 plus. Right? And so there's the reason this becomes interesting is on benzene, all the previous electrophilic aromatic substitution reactions I've shown were with benzene. All 6 carbons in a benzene are identical. In toluene, you've got the ortho positions. Those are different from the meta positions. And then you've got the para positions. So there's 3 different products we can get here. All right? The question is, which one do we get? Well, in this reaction, the aromatic is the nucleophile, the NO2 is the electrophile. Okay, so this is going to come down to getting the best cation. So let's go with this. I'll show ortho. So we put the NO2 there, H there, cation there. All right, this cation is actually delocalized pretty well. All right, the cation that you get with ortho nitration is delocalized all the way around the ring, and you get a tertiary carbocation as one of the structures. This is going to wind up being the same for para. And so you guys haven't worked with aromatic molecules enough, or benzene molecules enough, but electronically the ortho and para positions are the same. Remember, if you go back and look at this point, you should go back probably and look at the electron donating group and electron withdrawing group video. So if we put the NO2 plus in the para position, we get these resonance structures. Again, we get a tertiary carbocation there. That's going to be the more stable one. Right? Oh, there's a cation, sorry. All right, so again, 3 resonance structures and a tertiary carbocation is one of them. Well, what about meta? So we get this cation, we can delocalize that over here, and we can delocalize it to there. And there we go, those are our 3. We still get 3 resonance structures, but they're all secondary. All right, let me make sure these are all on the screen for you. Yeah, they are. So what this says is, the resonance structures you get, the intermediate for the ortho and para substitution is going to be easier than the meta. They're going to be more stable than the meta. And the other thing you can remember, an alkyl group is an electron donating group. So this methyl group is a weak electron donor. So this is going to be, if we look at this, you're going to put partial negative, right? You're going to delocalize the electrons on that electron donating group to the ortho and para positions. The ortho and para positions wind up being more nucleophilic. All right? And so I'm going to stop this video and I'm going to do another one on this and talk about it a little bit more with an electron withdrawing group. But the answer to this problem would be you're going to get both the ortho and the para. Okay? Statistically, there are two ortho positions. You might expect then there ought to be twice as much You might expect that there ought to be twice as much ortho because there are two different ortho positions that can react to one on para. But sterics favor over here. Honestly, in real life, you get a mixture almost every time. And so here's what I'm going to tell you. If you need to do one of these, if I gave you this as a homework, or a test or a quiz question, and you drew ortho, that's cool. If you drew a para, that's fine. If you need it in a synthesis, you can use either one. The only thing here is with a methyl group, an electron donor, it can't be the meta. All right, there'll be more on this.